Okay, so I'll just start with explaining what the while it's loading, what the objective of the seminar will be. So we will consider a toy problem with essentially, So we'll try implementing our own GANs on some toy problem where you have some 2D data set that you will generate essentially in your notebook. And then you will have to implement an assignment that consists of this multiple parts. The first part, you'll be required to fill in the gaps and to implement the code to actually train the simple vanilla GAN. With the first task will be to implement the standard objective for the generator, which is just essentially the second term of this binary of this classifier loss that we considered before. And the improved version of that, which is actually called a non-saturating GAN, and which was mentioned essentially in the first paper about these GANs, the Goodfellow paper. They proposed to use this term because it has some better optimization properties. It does not saturate, as the name suggests. And the second objective will be to just perform the same thing with this term. Then you'll have to implement Vasterstein GANs. So there will be two versions of that, and the links are actually provided. So you'll have to implement the original Vasterstein GAN with weight clipping. So you just each iteration you will clip the discriminator weights. And the second version is actually with gradient penalty, where you have to implement this gradient penalty with few modifications and plug it into the existing objective. So there are some useful links that you can use. For example, for weight clipping, you can check this link for GP. So you can just use some reference code in order to implement your own implementation of Vasterstein GAN. And the bonus task are Vasterstein introspective neural networks. This is kind of tricky. So if you have time and you want to try that out, this is actually a cool thing. So essentially, it keeps the discriminator the same, like in Vasterstein GP problem. But instead of generator, you will have the so-called fake data set of fake samples. And you will try to constantly update the samples by direct optimization over the samples. So just use the samples as parameters and try to make them as realistic as possible with some thresholds. So, you can take a look at the paper, and also these tips actually tell you what you have to do. And actually, you will be updating the data set of samples, and the newer samples will be more and more realistic. So the model will be trained like that. And so here, it's assumed that you can choose the number, the task number, which we're going to do in order to use that in your ifs and whatsoever later down the code. So here you have a sampler from real data, some visualization functions. Here you'll have to define architectures. For discriminator, just a reminder that you have to remove sigmoid layer. So you have to put some if here, depending on the task, whether to include the sigmoid layer or remove it. Because with sigmoid, it will, I believe, not work or work bad. Then you will have to define updates. So here you have to in this section, you have to write down the generator loss and discriminator loss. And it has to also depend on the task at hand. So depending on the number of tasks, you have to write different losses. So reminder, task 1 is just a simple GAN with Jensen-Shannon divergence. Task 2, the same GAN, but generator does updates via the non-saturating loss, which you can find at the beginning of the notebook. Task 3, 4, and 5 use Vasterstein GAN losses, so it will be the same objective, both for generator and discriminator here. And remember that the objectives have to be calculated as if you are minimizing them. So if some objective is maximized, you have to put minus this objective and calculate it here, minus the objective, For example, for discriminator, you're maximizing, so you have to put the minus. Don't forget that, or it will not work. So here you just sample some data points, and here is the main training loop. So you don't have to do any modifications to that, except when you are implementing Vasterstein GAN. So in Vasterstein GAN, you have to, in the vanilla version, you have to enforce weight clipping at some point before you update the discriminator, or gradient penalty as additional loss before you perform the step. And if you do Vasterstein introspective neural networks, you will have to replace that optimized G with your new optimization over this sampled set of data points. So, and this, well, you will have to uncomment in order to perform the visualization. And you can tune this number. Essentially, so what happens in Vasterstein introspective networks, you have the data set of generated samples, and at each step, you update this data set with more samples, for example, equal to the batch size. And when you train discriminator, you sample from that data set. And you can visualize essentially the history. So maybe 1,000, you can put a smaller number. I'll put like maybe 100 when I also start doing this notebook. And then, well, you can also summarize your findings, below. So here's the assignment. If you have any questions, you have two assistants and me who can help. Just raise your hand and we'll come. And later in the seminar, I will also start solving it, on the laptop. So you can also check your solution with the one that I propose to do. Just a quick note that if you have some troubles, so everything has to be working, but it's not working, try rerunning all the cells in the notebook. It probably has to do with, for example, you changing something in the training loop and not reinitializing the optimizer or something. Just rerun the cells and try again. And if that does not work, then, maybe you have a mistake. But so there are multiple things that may go wrong, so you have to reinitialize the networks, reinitialize the optimizer, and then try again. I now will implement the task 1 just to show you the visualization and what it actually means. So actually in the visualization, you get this, multiple Gaussians that you try to match with your samples, which are blue circles. And the lines actually correspond to the gradient dynamics that is provided by the discriminator, so where it wants to push every point on that grid. So I'm going to implement the first part and then show it on the projector. Well, probably you're smarter than me and you didn't get that error, but if you did, you have to average gradients before calling back, average loss before calling backward. So what this visualization actually shows you, it shows these Gaussians that are actually real data, and the blue dots are the sampled data provided by your generator. The arrows, they actually show you the gradient dynamics, so which point in this 2D grid discriminator wants to push where. So it's just evaluating the gradient of the discriminator at that point. So you can also see how well your model converges and where it actually wants to move your data point. As we discussed before, this is kind of the guide for the discriminator, where to push its samples. So for each line, the samples would like to be pushed in that direction. So it's kind of, thanks Dmitry Ulyanov for providing this notebook with this visualization. It kind of looks quite cool. And yes, so what you're expected to get is that over time, these blue dots have to group around these modalities and, kind of fill these Gaussians, which are the true distribution. So they have to kind of group around them, and that way you will know that your model is working. And also you can visually compare the results that you got from different GANs that you actually tried. So some of them may work better than the others, and you can see that in the visualization after you run this optimization process. Okay, so I'm going to just try to memorize the result we got here. So we got the collection of points in between these different Gaussians, and actually the gradient dynamic, it kind of shows you that if the sample arrives somewhere in the middle, the discriminator wants that sample to be pushed towards the closest the closest modality in this true Gaussian distribution. So it's kind of the picture that we actually want to see, that these arrows are pointing from that low probability space in the true probability distribution to the high probability space. And now I'm going to implement the second part with non-saturating GAN, and we'll see what results we get. Maybe we get, well, something better than this. So the point of applying non-saturating GAN is actually the following. So as we have seen in the previous picture, we had like this perfect picture that the discriminator have, well, trained perfectly in order to actually separate these values. So it's want to push the values, well, the samples to stop appearing in the middle of this, modalities. But on practice, what happened is that generator still kept producing the samples because, well, the objective that it tries to optimize actually saturates, and it does not receive any gradients from these points in the middle. So it keeps, well, it actually receives no feedback on whether to keep these points, keep sampling points in the middle of these modalities, or, well, to actually push them towards the high probability regions. And hopefully in the non-saturating GAN will help us address that issue, because the gradient flow to the generator is, well, a little bit smoother, and hopefully it will learn to actually sample only in these modalities. It seems my collab got disconnected and we have to run it all over again, but well, I don't know if we have time. Probably I'm going to solve the third task about Vasterstein GANs and show you the solution. Well, so non-saturating GANs did not train till convergence. I believe there was like 700 iterations. It was still kind of bad, but the previous example was 1,000 iterations, so maybe it would actually converge, but my collab did disconnected. So kind of started running all over again. So now I will be implementing the weight clipping for Vasterstein GANs. So for Vasterstein GAN, you have to put this if inside the discriminator, because you don't want the output ending, the discriminator ending with sigmoid. Well, there are reasons for that. Probably it's required to have negative values in your objective. So in Vasterstein GAN objective, you are assumed to have the real valued output of the discriminator, and the sigmoid actually maps it into an interval from 0 to 1. So it may work unstable if you do that. So just remember to remove the sigmoid. So since both of the networks are solving minimization problems, and the output of the discriminator can be treated as a realism score. The higher is the output, the more real the discriminator considers that particular image. So for the generator, we want to maximize the realism score, which results into the minimizing of the minus realism score for the fake images. And for the discriminator, we have to just calculate the difference between these two expectations. And again, in order to make the signs correct, so discriminator wants to maximize, it wants to minimize the realism score for fake images, so it's with plus, and it wants to minimize this realism score for real images, that's why it's with minus. But that's just a tip about how to, well, put the correct signs. Actually, it's just the Vasterstein objective. It's like two expectations which we evaluate here, the difference between them. Okay, so if we take a look at the code, which is referenced in the notebook, so here they perform the gradient clipping over here. It is done before we do the forward and backward passes, but you can do it after your iteration. So like in the paper, for example, I'll just do it before the iteration. So we have to iterate over all the parameters of the discriminator and clamp them. This operation is not differentiable, and this is why we don't really expect that weight clipping to work. But the next Vasterstein gun, the one with gradient penalty, should actually work better. So I'll just insert it here before the optimization starts. The optimization step starts. So I believe for lower and upper values, we have in the assignment 0.01 minus and plus. And I guess it should work now. So again, what actually happens here, so we want to make our function Lipschitz continuous. And a hacky way to do that is just to constrain the output of the function. So again, Lipschitz continuous means that for any two inputs, the difference between the outputs is less than equal than L times difference between the inputs. And in order to constrain that, well, the function that would always return 0 or any constant value is Lipschitz continuous. And in order to make our function become closer to 0, so don't change the values by a large margin, we introduce that weight clipping. So we can't guarantee that this function becomes Lipschitz 1 continuous exactly, so there are no guarantees. This is just a way to somehow bound its output, a pretty hacky way. So from what I can tell, this practically is the result that you're expected to get. The discriminator is kind of bad. So as you can see, it kind of learned the some hyperplane in that space, essentially a line, and it tries to push the samples away from that line. So behaves poorly, and well, we expect that because this trick is too hacky. It's just weight clipping with, well, no gradients associated with that, and maybe it's also not a good idea to use Adam, because Adam keeps the running estimates of the momentum and variance, and well, the weights keep constantly changing, so maybe SGD would be a better candidate for the optimization method. But let's just continue and try to do the more proper Vasterstein gun with gradient clipping. A gradient penalty, yeah. So for the gradient penalty Vasterstein gun, the losses remain, well, completely same. So we don't change them. We just change the way we, well, in that case, we don't try to make it Lipschitz continuous. We just try to penalize the gradient. As I said before, we can do that because the optimal solution of this dual problem, which gives us Vasterstein distance, actually has that property that the norm of the gradient is equal to 1 almost everywhere. And essentially, we're trying to enforce that at least on the convex hull between the real and fake data points, around the real and fake data points. And for that, well, it's not required probably to re-implement it from scratch because it's quite a complicated function, so this gradient penalty. But I will just go through it to actually explain what each part means. So in the objective, we're asked to apply this penalty on the we may say convex combination between real and fake data points. So we just sample random values from 0 to 1 and just get something in the middle between each real and fake data point. So we just, essentially draw the line between the 2 points, do samples, and pick at random some sample on that line. If you're trained on images, it actually corresponds to some middle image, well, averaged image between some real and fake image, for example. Then we calculate the output of the discriminator given these inputs. And then we would like to calculate the gradients with respect to the inputs of the discriminator. So for that, we just use this grad function. We set the outputs as the outputs of the discriminator, inputs as the inputs of the discriminator. And well, this function is, since it assumes backpropagation algorithm. Well, it's kind of a part of the backpropagation algorithm, so it assumes some gradients to be fed to it or with respect to the output. But the gradients with respect to the output are are ones, because it's like, well, it's a final part. We don't have any other modules which are applied, which use these interpolates as input, so we just feed once. No, and then we just, well, calculate these gradients and use them in order to apply the penalty. So we calculate second norm, subtract 1, second power of 2, mean, and apply lambda. Lambda you can set from 1. In the paper of Weston Gans, it was set to 10, I believe. So it's up to you. It's actually a tunable parameter. And so we will just copy-paste that into our code. And now we have, before we do optimize step with respect to the discriminator, we have to also calculate this gradient penalty. We can do it like that because backward just accumulates the gradient in all the trainable parameters. So we don't have to add it up actually. Let's see if it works. So it should work considerably slower because you actually do 3 forward passes through the discriminator instead of 2, because you do a forward pass for real samples, for fake samples, and now you also do this forward pass for interpolates. But in the end, we should get, well, quite good results. And also, it kind of tends to drift between the iterations, but so it means that the intuition that was obtained by us via this simple optimization problem, where we had a single parameter generator in the single parameter discriminator, and well, people that wrote the paper found out that Vasterstein gun actually goes on the orbit. This intuition is true, so don't be surprised if it kind of starts drifting around by not changing the distribution of fake samples by a lot, but just kind of drifting. It means that you have reached this orbit. All right, so let's try to implement the last bonus assignment now. So first of all, I'm going to open the paper for the reference. So we're going to reuse all the objectives that we had defined before, alongside with gradient penalty, I suppose. Yeah, it does use gradient penalty. And what? Yeah, it's actually, yeah, it's missing because I had to. Yeah, I will fix that. I tried training it without gradient penalty, but in the paper in the paper they suggest to use it. I'm going to fix this. Well, there are official solutions by me on the GitHub, and this solution is missing the gradient penalty applied to introspective networks. So I'll have to fix that. But let's take a look at the algorithm. So it looks like that. We just sample, well, for k steps, we'll just ignore that. We'll just do one step as we did before. It's just suggested for Vasterstein Gans to do multiple steps of discriminator per one step of the generator, but for simplicity, we didn't do that. So we just sample positive examples, and then we sample the so-called pseudo-negative examples. So essentially, we got this data set S, which is actually a data set of fake samples, and we keep updating it. So when we train the discriminator, we just sample these examples from the data set and perform a standard SGD or ADAM in our case, using the standard Vasterstein GP objective. But then the interesting part happens when we do the synthesis step, the generator training step. Instead of that, we just sample a little bit more samples from some simple distribution, for example, a normal distribution. So, each component is sampled independently. And then we perform SGD with respect to the samples. So we try to make the samples more realistic using the currently trained discriminator. And of course, if you train till convergence, you will overfit, because the discriminator is not perfect. You can easily fool him if you train long enough. But here there is a trick that we just perform early stopping, so we stop before we overfit. And then the samples that we have optimized with respect to, we'll just put them into this data set of fake samples, so we update it. And then on the next step we will sample already from a bigger data set. So the idea is kind of like that. And the idea is that the samples that we put later on in the optimization process in the data set will be kind of, already like good fake samples. So we'll have to obviously throw away samples in the beginning because we used the discriminator that was not trained yet. But in the end, we should get good samples. So let's implement that. So, okay, obviously the optimizer for the generator will be a bit different. So I will initialize this data set with some random noise. I will expand this data set with like a handful of samples, just a batch size. And so when we try the discriminator instead of this, let me modify that. So instead, we just want to sample from this data set of generated samples that we'll keep updating. So in the case of first iteration, we just take all the values, but later we will, since the data set will be expanding, we'll take the values from different iterations. So I don't know if I did that correctly. We'll just have to figure out when we run the whole thing. But the idea is that we just sample from this data set a batch size number of samples. Okay, and now here, instead of performing optimization of the generator, we'll just perform something different. So first of all, we need to sample some new samples that we're going to optimize with respect to. So we will initialize them as nn.parameters so that they would have gradients to be, requires grad flag already set. Then we'll just define optimizer over these parameters. I don't know if it makes sense to use Adam here, but well, why not? Well, okay, so we initialize the optimizer to optimize these parameters, and now we just have to constantly evaluate this loss and perform that until we hit the stopping criterion, which I'm going to implement just a little bit later. Okay, so this is the training loop, but we need somehow to get out of it at some point. And what is suggested in the paper is that we perform stochastic gradient descent with early stopping. Well, first of all, we also need to add epsilon to the gradients. And well, epsilon has to be sampled from the is time varying step size. Okay. So from some noisy distribution. So I don't know if I'm correct, but I believe that you can do just that. So to just add to the fake scores, and then when you backpropagate, your gradients will be noisy. We just add some noise with the small variance. And now we have to perform early stopping, and it is explained here. So they suggest to measure the minimum and maximum scores of positive samples, and then sample the early stopping threshold uniformly between these two values. And when your loss reaches that threshold, you have to get out of the cycle. So let's calculate the value of the threshold first. We need real scores for that. So we sampled the value, the threshold, and then in that cycle, if I prefer to control it via mean, so okay. Here, let's put it like 100. And let's hope it works. Probably does not work, of course. Okay. It seems like you don't need to do. Oh, it already gives you random permutation, so we have to put just the maximum value, right? Over here. Like this. No, it does not work. Fake data is not. Yeah, it should be indices. Something is working. Okay, so basically what we expect with time, we expect the samples to actually fill in these high probability regions, because we keep updating the data set and we visualize only the latest samples. Well, I don't know if I actually did everything correctly, but in the notebook which is posted as a solutions, it has to be implemented correctly. I just need to fix the gradient penalty not being applied. It's not being applied even here, so let me fix that as well. The question was why this task is much slower at being optimized. Well, because we actually optimized still convergence in this loop. We have while true. Okay, I have some bug again. So, well, the seminar is actually over, at least time-wise, but you can still stay in order to see if it actually works. Well, or you can go to the break.
Could you maybe give a quick summary of how the results should differ between the 5 tasks if everything works correctly, like in terms of convergence speed and in terms of quality of the results?
Yeah,
because for me, for example, the third task didn't quite look so good, so I was just curious what was maybe going on.
Yeah, so in the perfect world, I would do the ranging that the idea is that non-saturating GAN actually works quite well. And so it has to outperform essentially all the other methods. Vasterstein GAN without gradient penalty with weight clipping should actually perform poorly because it's a bad way to actually do it. You don't clip the weights of your network. That's a bad idea. But the gradient penalty one has to perform well, but it kind of starts drifting at the end around the orbit. So, you have to kind of use it when you have a little data in your problem. And here we have like 100K samples, 100,000 samples. So maybe if you could reduce the number of samples, I would suspect that Vasterstein GAN would start performing better. And the last is just a cool thing. It's probably works the worst of all examples, but it's still cool that you can actually ditch out the generator whatsoever, and it still will kind of work. Yeah.
Thank you.
So yeah, that's the summary of the seminar. Yeah. If you have any more questions, feel free to ask. If not, then, thank you for attending.